then what we're interested in the interval from t initial equals 1 second, t final equals 3 seconds. We're interested in what x was initial to final as well. So x initial would be whatever we have at 1 second. It would be 21 plus 22 times 1 minus 6 times 1 squared. Which would be 43 minus 6, or 37. And x final position would be 21 plus 22 times 3 minus 6 times 3 squared. So that'll be 87 minus 8 times 6 times 9. Right? So, our displacement is the final position minus initial position. Will be 33 minus 37, or negative 4. And our change in time will be final time minus initial time. 3 minus 1, or 2 seconds. This x is in meters. So our velocity, average velocity, the displacement over time, can be a negative 4 over 2, or negative 2 meters per second. Total displacement over total time. So far, so good? Take a look at number 2. The bullet is fired through a board 14 centimeters thick with its line of motion perpendicular to the base of the board. It enters with a speed of 450 meters per second and emerges with a speed of 220 meters per second. What is the bullet's acceleration as it passes through the board? Well, for our purposes, we said that we're only going to deal with constant acceleration. So, with that in mind, average acceleration will be the same as instantaneous acceleration. So our average acceleration is the change in velocity or the change in time. And we'll use that in this case. So we're given that actually we're better off not even going with that definition.
You got to go with kinematic equations.
Go with kinematic equations. So, since we're at that point, let's write down all the kinematic equations for the moment, just for review. First one was final velocity equals initial velocity plus acceleration times time. Second one, displacement equals average velocity times time. Just kind of a rewriting of this definition. Or we could write this average velocity as final velocity plus initial velocity divided by 2 times time. So that's average velocity as well. Final plus initial divided by 2. At least under constant acceleration. Third one was final velocity squared equals initial velocity squared plus 2 times acceleration displacement x. Fourth one, delta x displacement equals initial velocity times time plus 1/2 acceleration times time squared. And the fifth one Also displacement equals final velocity times time minus 1/2 acceleration times time squared. 5 kinematic equations. Each one has 4 kinematic variables, missing the 5th one, and that might help you decide which one to use in which situation, depending on what you're given in the problem. So in this particular problem number 2, the bullet is fired through a board 14 centimeters thick, enters with a speed of 450 meters per second, emerges with a speed of 220 meters per second. What's the bullet's acceleration? What do I know? What is given in this problem?
Initial velocity, final velocity.
Initial velocity, final velocity.
Trying to find acceleration, yeah, X.
All right, so we got initial velocity, 450 meters per second. Final velocity, 220 meters per second. Brad said, we're also given displacement, because we're going to figure this out over the thickness of the board, which was 14 centimeters thick. Let's put that in meters, 0.14 meters. And we're asked for acceleration. So we use kinematic equation number 3. Final velocity squared equals initial velocity squared plus 2 times acceleration, displacement x. Solve this for acceleration. So we'll have 2 acceleration delta x equals final velocity squared minus initial velocity squared. Acceleration will be final velocity squared minus initial velocity squared over 2 times displacement delta x. And that will be 220 squared minus 450 squared over 2 times 0.14. Pretty good? 550,000? Negative, right? Bullet's going to be decelerated at negative 550,000 meters per second squared. It'll be a negative 550 kilometers per second squared. So already those equations are coming into play. It's kind of nice, so we don't have to worry as much about the other stuff, just those 5 equations. Before I do some of these other problems that were requested, let's continue to warm up with some problems that are not as challenging. Take a look at number 12. The rock is thrown downward from an unknown height above the ground with an initial speed of 10 meters per second. It strikes the ground 3 seconds later. Determine the initial height of the rock above the ground. Alright, so you're going to throw a rock down. You don't know what your height is, but you do know that you're going to give it an initial speed of 10 meters per second. We're going to throw this down to the initial speed 10 meters per second. strikes the ground 3 seconds later. Your time is going to be 3 seconds. The question is, determine the initial height of the rock above the ground. Now list the 2 of the things that were given. In order to do any of these kinematics, we need to know 3 things, and then find the 4. So the third thing on this problem would be, Sosin said, acceleration. We know the acceleration of gravity, or acceleration down. Gravity is 9.8 meters per second squared towards the center of the Earth. Of course, my next challenge is to decide whether this acceleration is going to be positive or negative. It's going to be positive. Why? Because I'm going to choose the direction that my initial velocity is going as my positive direction. So I'm going to say that this is going to be a positive value, that's going to be a positive direction. If that's a positive direction, then acceleration in that direction will be a positive quantity. And I can think of it intuitively as well. I mean, if I were to throw this down, it's going to pick up speed before it hits the ground. So my intuition tells me that's going to be a positive acceleration in relation to my initial speed. It's going to increase the speed of the ball. So it should be a positive quantity. So acceleration will be 9.8 meters per second squared. What's the 4th variable in this problem? Delta y, because we're actually asked for how high it was. So we really want to know what this delta y is. Well, just for grin, let's put in final velocity in there too, just to be complete. What is the final velocity?
0.
Final velocity is 0, eventually. Can I use that to my advantage? Can I say final velocity is 0 and solve the problem? Why not? Because it bounces first?
It doesn't help to figure out delta y. If you do figure out delta y, then
You can use the 4th equation, delta final velocity.
I don't need the final velocity to solve this equation correct. I mean, I already got 3 things, I know. So, I mean, I can use the 4th equation to figure out delta y. So I can get delta y. So I don't need to know that the final velocity is 0. But if I did know that final velocity was 0, it would be nice because then I could use, I wouldn't be limited to just the 4th equation. I could use, 4 different equations. However, why can't I say the final velocity is 0?
Because when the final velocity is 0, then your acceleration is not 9.8 no more.
Exactly.
Acceleration is deceleration by then.
Exactly. And if I say the final velocity is 0, I'm looking at the ball after it's struck the ground. Once it strikes the ground, all bets are off on constant acceleration. I can only use these equations when acceleration is constant. Once there's another force that comes in, that changes the acceleration, and my kinematic equations are no longer valid. So, I mean, I could figure out maybe the average velocity or average acceleration or something on the contact, but I can only talk about the interval of time and the interval of motion up to exactly the point right before it hits the ground. Once it touches the ground, then kinematics are out. These equations are out. So really, truly, my final velocity, I would not say 0. I would say it's going to be some value that's greater than 10. It's going to be the value of the final velocity right before it hits the ground. And that would be the final velocity that I would want if I were to solve this problem. All right, so let's go back to the idea that we got 3 of them and we want the 4th. And so we have displacement y equals initial velocity times time plus 1/2 acceleration times time squared. That's my formula, and if I were to work out these problems, I would start with the formula, whatever formula I want to start with. I wouldn't try to do it all in my head, or I wouldn't try to jump into putting numbers in right away. I mean, just write the formula algebraically as it should be. Don't put in any negatives, or if there's no negative sign, just write it like this, and then put your quantities in there afterwards. Some of them might be negative, in this case they're not. But. All right, delta y equals initial velocity 10 times time 3 plus 1/2 times acceleration 9.8 positive times 3 squared gives me 74.1. Did we do this problem before?
Yeah.
We did. Okay. Probably say the same thing too, right? Once it hits the ground, all bets are off. .1 meters. Let's figure out what the final velocity is. Since we already did this problem, let's do something new with it. How would I figure out the final velocity? Any of the 4 equations that have final velocity in it. So anything but this equation. Probably the easiest one is this equation number 1, once I know what I know. So let's try that. Final velocity equals initial velocity plus acceleration times time. It would be 10. It's 9.8 times 3. It would be 29.4 plus 10, 39.4 meters per second. So neglecting the air friction, terminal velocity, final velocity of this ball right before it hits the ground is 39.4 meters per second. Okay. Let's try a few problems with this. Take a look at problem number 8. The ball is thrown vertically upward with initial speed of 20 meters per second. 2 seconds later, a stone is thrown vertically from the same initial height as the ball with an initial speed of 24 meters per second. At what height above the release point will the ball and the stone pass each other? All right, so we're going to throw the first ball with an initial velocity of 20 meters per second. Let's call this ball A. And 2 seconds later, a stone is thrown vertically up, which is called another ball, with an initial speed of 24 meters per second. So 2 seconds later, we have B, initial velocity of 24 meters per second. I really should have left myself some boardroom so I could show what was going to happen up above. At what height above the release point will the ball and the stone pass each other? Okay. What do I know on this problem? let's look at ball number 1, for instance. What is given in that problem?
Velocity, acceleration.
Velocity and acceleration, right. Initial velocity and initial acceleration. So let's say in problem number 1, or for ball B, for ball A, we know that the initial velocity is 20 meters per second. And the acceleration is negative 9.8 meters per second squared. Irvin, why negative?
Because we chose the initial velocity.
Because we chose the initial velocity upward to be positive. And so that would mean that gravity, which is 9.8 meters per second squared down, would then be defined as negative. It's going to slow the ball down, actually. All right. Anything else I know?
Time would be t plus 2.
Where t would be the time for the second point, right? That's a good point. Let's say that time for A will equal the time for B plus 2. We're going to have 2 extra seconds for that. All right. Let's just say go some displacement delta y. I don't know what that is. Let's call it delta y A. All right. We only know 2 things, so we can't solve for this directly. And we need to know 3 things in order to solve a kinematic equation for just one situation. So we're lacking some information here. Let's look at ball B. What do we know about ball B? Time, initial velocity, 24 meters per second. Acceleration is negative 9.8. Same. Negative 9.8 meters per second squared. Displacement, delta y b. Similar type problem. We don't know, when we know 2 things, we don't know a bunch of other things. However, we don't know, we need one more thing that we need to know to solve one of these problems. But if we combine the 2, we can see that there's some things we can use. One thing is delta YA should be the same as delta YB, because in the statement of the problem, at what height above the release point will the ball and the stone pass each other? So at that moment, they will have the same displacement. And we also have a relationship between the time. All right? So, take a look at this. If I were to write an equation for the motion of ball A, I would say that displacement YA equals initial velocity A times time for A plus 1/2 acceleration times time for A squared. Something like that. And so I could say displacement YA is equal to 20 times time for A plus 1/2 times negative 9.8 times time for A squared. That's about as far as I can go. If I wrote my equation for ball B, I could say that displacement for ball B is equal to initial velocity for B times time from B plus 1/2 acceleration times time for B squared. So we could say this is equal to 24 times time for B plus 1/2 times a negative 9.8 times time for B squared. But we're going to say that displacement YA equals displacement YB. Because the ball and the stone will pass each other. And we're also going to say that time for A is time for B plus 2. So we're going to have 20 times time for B plus 2 minus 4.9 times time for B plus 2 squared equals displacement YB, which would be 24 times time for B minus 4.9 times time for B squared. All I did was set the two deltas equal to each other and substitute in for the time for A. I now have one equation with one unknown. It's solvable. We're going to have 20 times the time for B plus 40 minus 4.9. This will be time for B squared plus 4 time for B plus 4 equals 24 time for B minus 4.9 time for B. 4.9 time for B squared. Cancel out both sides, which is kind of nice. And so now I have 40. 20 time for B minus 4 time for B will give me plus 16 time for B. And then minus a, oh no, I got 4.9 times that. Better be careful. All right, 20 time for B plus 40 minus 4.9 times 4 time for B would be 19.6 time for B minus 19.6, 24 time for B. Right? So what do I have? Let's see. I got 24, call it 24 time for B minus 20 time for B plus 19.6 time for B equals 40 minus 19.6. Okay? What am I missing? And I switched the equals around. So because I put my time for B over here, so I kind of switched it around like that. Right? I don't know, let's see what we come up with. So we got 4 plus 19, so we got 23.6 equals 20.4 Time for B is 20.4 divided by 23.6. It's 0.864 seconds. Nice to know, but we still haven't solved the problem yet. Because the question was, what was the, at what height do the two pass each other? And so we really want to find delta YB in a sense. So, delta YB is initial velocity B times B plus 1/2 acceleration time of B squared. There's 24 times 0.864 plus 1/2 times negative 9.8 times 0.864 squared. We get 17.07 meters.
Like I was wondering whether or not the first ball was going to go up and stop and then come back down while the second ball was still going up. So was we just automatically just to assume that, you see what I'm saying, that they were just going to continue up?
No, we didn't assume any of that. And in fact, we didn't have to know that.
We didn't have to know that?
Yeah, because as the problem was stated, we don't have to, we can find out, but we don't have to worry about whether it's on the way up or on the way down. Because all we want was strict displacement from where we started, that they had the same height. So it's possible that one actually goes up and starts to come down. In fact, let's figure out what they do. The time for A is 2 seconds longer, right? And let's see how long it would take to go up to maximum height. Let's do it that way. Let's say if you're to throw at 20 meters per second against gravity, how long will it take to reach maximum height? Can I do that problem? I can, because, all right, let's figure out.
So would you make V final like some real small number?
Yeah,
Okay,
really
zero.
small number. I'll make V final 0.
Really?
Because when it reaches maximum height, it momentarily stops. So I'm going to say my initial velocity will be 20. My acceleration will be a negative 9.8. And my final velocity will be 0. What's my time? If I were to fill, how long is it going to take before it reaches maximum height? Well, velocity equals initial velocity plus acceleration times time. So time will equal final velocity minus initial velocity divided by acceleration. That will be 0 minus 20 divided by negative 9.8, which would be 2.04 seconds. Interesting, because in this problem, time B was 0.864 seconds, time A was 2 seconds plus that, so the total time for the first ball is 2.864 seconds. What the first ball did was it actually went up to maximum height and started to come down, because maximum height only took 2 seconds, or 2.04 seconds. and the second ball was on its way up. So the first ball went up, started to come down, the second ball was on its way up. They had the same displacement, same height momentarily, but one was coming down, one was going up. Yes? Good question. If we plug in time for A, will we get the same answer? Hopefully we will. But let's see what we get. It's always educational to just try it out. So here's the idea. Time for A is equal to 2 plus the time for B. That's going to be 2.864 seconds. Let's find out what the displacement for ball A is. So we say delta y A would equal initial velocity A times time for A plus 1/2 acceleration times time for A squared. This would be 20 times 2.864 plus 1/2 times a negative 9.8, 2.864 squared. What do we get? I got a little mark on my calculator, so I know this is decimal point or what. Let me just do that. Within round off there, there's actually two things going on here. I mean, if we didn't have acceleration, it would go pretty high, right? But then you got the acceleration, which is providing a negative motion, and the combined motions actually bring it down. Fun? Problem number 10 was one of the ones. Take a look at problem number 10. It's kind of somewhat similar to this problem. An object is thrown downward with an initial speed of 10 meters per second from a height of 60 meters above the ground. At the same instant, the second object is propelled vertically upward from ground level with a speed of 40 meters per second. At what height above the ground will the two objects pass each other? All right, so the first object is going to be thrown downward with a speed of 10 meters per second and at a height of 60 meters. I'm just going to call it H for the moment. And at the same instant, the second object is propelled upward with a speed of 40 meters per second. question is, at what height will the two objects pass each other? So at some point, there'll be some arbitrary height. Let's call it, since we're looking this way, let's call that delta y b. That's what we'd be interested in. And it would be delta YA from the 60 meters. All right. Before we get there, let's talk about what we know about each ball thrown. Okay. What do I know about ball A? Sorry. I know the initial velocity is, okay. Initial velocity for A is 10 meters per second. And we're going to call it positive downward. And so acceleration would be positive 9.8. What else do I know, or do I know anything else? You're right, I don't know anything else. So let's just say, let's give it some variables. I don't know time, let's just call it t. All right. I don't know displacement. Let's call it delta YA. That's this distance right here. All right. What do I know about ball B? Initial velocity is 40. Acceleration is negative 9.8. So it's different if I'm going to describe it in terms of what it's doing. Okay. Time, I don't know, but
It's gonna be equal to,
it's the same time as this. That's probably one reason why I didn't give this a subscript. It's going to be the same time. I'm doing it simultaneously, right? What I could have done that A and B problem over there is, like, you know, instead of calling time B and time A, I could have just said that, I would have said time A equals t plus 2. I could have said time B, which is t. But in this case, the time is the same. T is the same. Which is nice. What about displacement delta YB?
it's gonna be 60 minus delta y.
Right. It's going to be 60 minus delta YA, or let's go the other route. Let's do it for delta YA. So let's say, because delta YB will give us immediately what the height we want. So let's keep that one. And then delta YA would be then 60 minus delta YB. Delta YA is going to be this displacement there. And that's going to be 60 minus delta YB. Whatever delta YB is, it's going to be delta YA. So let's try and describe these two motions with equations. If I look at ball A, I would say delta YA is equal to initial velocity A times time plus 1/2 acceleration times time squared. And so I would write this as delta YA equals 10 times time plus 1/2 times 9.8 time squared, or delta YA equal to 10t plus 4.9 t squared. Don't know t, don't know delta YA. I look at ball B, I would say delta YB is equal to initial velocity v times time plus 1/2 acceleration times time squared. 40 times t plus 1/2. For v, the acceleration was a negative 9.8. So this would be 40t minus 4.9 t squared. Same t. I do know that delta yb is equal to 60 minus delta ya. That's going to be my key in this problem, related, and also the fact that time is the same. Well, let's set those equal. So I have delta yb was 40 minus 4.9 t squared equals 60 minus delta ya 10t plus 4.9 t squared.
What happened with the T with 40?
Oh, I missed something.
Just to see.
40?
Oh, yeah, 40t, I'm sorry. That's the only thing in this? Yeah, that would be critical. All right, so what do we got? We have a minus 4.9 t squared on both sides, so that's going to be gone. 40t equals 60 minus 10t. 50t equals 60. T equals 60 divided by 50. 1.27.
I thought you had a minus T and T. Oh, okay, yeah.
Question was, what was the height at which they passed? So let's find delta yb. Delta yb is equal to 40t minus 4.9 t squared. That's going to be 40 times 1.2 minus 4.9 times 1.2 squared. Let's figure out what that is. .94 meters. This is not an easy problem. This would be one of the harder ones, I think. Because the hardest part of it, what makes it hard, is trying to relate the two motions. I mean, if you're not given enough information, you're not given the three variables that you need, then you have to do something like solve two equations with two unknowns. Because if you have the same number of equations you have as unknowns, then you can solve it. And that's basically what we're doing here. Is we only know two things. We have two unknowns and two equations with those two unknowns we can solve. Take a look at, maybe some of these other ones aren't so bad. Take a look at 13. A ball thrown vertically from ground level is caught 3 seconds later by a person on a balcony who is 14 meters above the ground. Determine the initial speed of the ball. Do I move around a lot, Matt? It'd just be nice. Ball thrown vertically from ground level is caught 3 seconds later by a person on a balcony. I'm saying basically this person's underneath the balcony, 14 meters above the ground. Kind of romantic thing to do on Valentine's Day, throw a ball into the balcony. Determine the initial speed of the ball. All right, so what do we know about this problem? What's given?
The Y, the
Nope.
time,
Not the y, 14 meters.
the time,
Time is 3 seconds.
acceleration.
Acceleration is negative 9.8. Why negative? Because we define upward as positive. Very good. So there we have it. 3 kinematic variables. And we want to find the initial speed. All right? So maybe we can do it. Hopefully we can do it. With that given as such, what equation should I choose? Number 4. All right, so let's try that. We have displacement equals initial velocity times time plus 1/2 acceleration times time squared. We want to solve this for initial velocity. So we have initial velocity times time is equal to displacement minus 1/2 acceleration times time squared. Our initial velocity is displacement minus 1/2 acceleration times time squared divided by time. So that's going to equal 14 minus 1/2 times a negative 9.8 times 3 seconds squared over 3 seconds. So negative negative is going to be positive. So this will be 14 plus 4.9 times 9 over 3. $19.436. When I throw that ball, is it on its way up or is it coming down? How can I find out? Question is, when the person catches the ball, do they catch it after it reached maximum height and started on its way down, or did they catch it on the way up? So was the ball going up or down when they caught it?
Can't you plug in 0 for the velocity and off the time and see if it's grand?
I could. That's all right. Let's do that. Let's try. Let's see how much time it would take to go to maximum height. Okay. then we would say that our final velocity would have to be 0. Our initial velocity, which we just figured out, is 19.36. And acceleration would be positive or negative 9.8. Negative, right? So what's the time to maximum height? So we're going to use kinematic equation number 1. Say final velocity, initial velocity plus acceleration times time. Final velocity in this case is going to be 0. Solve this for time. Time will equal negative initial velocity divided by acceleration. So it'll be a negative 19.36 divided by a negative 9.8, which will give me 1.976 seconds. Hence, I can conclude that this ball was caught on its way down. Correct. Because if it took 1.976 seconds to reach maximum height, and we actually threw it for 3 seconds, then it's on its way down. Let's try another thing. If my final velocity after 3 seconds was positive or negative, that would tell me whether it was on its way upward or down too, right? If I say up is positive, then if my final velocity after everything is done is a positive value, that means that it was on its way up. If my final velocity is negative, that means it was on its way down. Let's try that. Let's see. We start from our original data over here. And I would say that final velocity equals initial velocity plus acceleration times time. I would say that'd be equal to 19.36 plus a negative 9.8 times 3. Gives me a negative 10.0. Which means when the person caught it on the balcony, the velocity of the ball was a negative 10 meters per second. The negative meaning that it was actually on its way down. Here's an interesting sidelight to all that, which might go in the category of more information than you need at this moment. But in the absence of air friction, the motion of going up is exactly mirrored by the motion coming down. So that if I were to throw a ball up, it would start off pretty fast and then slow down under acceleration, slow down to a stop eventually. And then from that point, it would start to accelerate, pick up speed, and come down, and then I would catch the ball. At any particular height in that motion, the magnitude of the velocity going up is equal to the magnitude of the velocity coming down. In other words, the motion up is exactly mirrored by the motion coming down. It's going to start out fast, slow down to 0, start at 0, speed up. When I catch it, and I catch it with the same speed that I threw it with, neglecting air friction. So if I throw it as hard as I can, it's going to come down and hit my glove if I'm playing baseball with the same speed. So almost as if I had just thrown it right into my glove. Okay. So in this particular case, when she catches the ball on the way down at 10 meters per second, on the way up, when it passed her, it was moving at 10 meters per second. Yes. What's that? Exactly mirrored.
This one,
14. Problem number 14. When starting from rest at the bottom of a straight road with constant upward slope, Joan bicycles to the top 50 seconds ahead of Sally. his travel time is 5 minutes. What is the ratio of Joan's acceleration to Sally's acceleration? Bottom of a straight road with constant upward slope. Joan bicycles to the top 50 seconds ahead of Sally. Should quit while I'm ahead. And Sally's time. I don't think these pictures are really going to help me on this problem. All right, so what do I know? Let's look at Joan and Sally. Bottom of a straight road with constant upward slope. What would that tell me? Yeah, the same gravity. You know, we don't know the actual value of that because we're going to learn that it's going to be a fraction of gravity. But since it's the same slope,
Velocity is constant.
maybe not. Maybe not. But we do know the acceleration is constant. We'll say that they got the same acceleration. What else is the same for both of them?
You said they got the same acceleration.
Oh wait, no, they don't have the same acceleration. That's right. Velocity not. Is velocity constant? They have the same acceleration of gravity, but actually they're going to travel against gravity, so that it's insignificant.
All I saw was that, the time.
Yeah, time is the
Okay.
Don't
So
they have the
time.
same displacement though?
There we go. Who said that? Same displacement. So let's say displacement here, it's called delta x for Joan, is equal to displacement over here, delta x for Sally. That's going to be useful. So instead of time, Sally's time was 5 minutes. So time for Sally is 5 minutes, which would be 300 seconds. Joan's time is 50 seconds ahead of Sally, so that would be 250 seconds. What else do we know about both bicyclists?
Final velocity would be even.
Final velocity, or
They got to where they were going. After they went there for 5 minutes, they stopped. They didn't stop.
no? This is a good debate. You're right, presumably. Maybe they just race towards the finish line and pass right through.
So,
But, yeah, I didn't put what was down here below. The woman-eating shark. But makes it a little bit more interesting, doesn't it?
They better stop there.
We could probably say that their initial velocities were the same, because they both started from 0, right? So initial velocity here for Joan is 0. Initial velocity here for Sally is 0. We want to find the acceleration for Joan and the acceleration for Sally, at least some relationship between the two. All right, so let's try. Let's see what we get if we write down the formulas for these two motions. If I look at Joan, I would have displacement for Joan equals initial velocity for Joan times time for Joan plus 1/2 acceleration for Joan times time for Joan squared. And in this case, acceleration is something we need to find because, and it's independent of gravity per se because they're doing their own thing. And they're doing their motion up this slope with whatever displacement per time. Initial velocity is 0, so that's going to help. So we have displacement for Joan equals 1/2 acceleration for Joan times time for Joan squared. Look at Sally. We would have displacement for Sally equals initial velocity for Sally times time for Sally plus 1/2 acceleration for Sally time for Sally squared. Initial velocity is 0, so we have displacement for Sally equals 1/2 acceleration for Sally time for Sally squared. What's my next step? Put them equal to each other because they go the same displacement. So displacement for Joan equals displacement for Sally. They're going to go the same track. So we'll have 1/2 acceleration for Joan times time for Joan squared equals 1/2 acceleration for Sally time for Sally squared. Multiply both sides by 2, get rid of the 1/2. And so state what's the ratio of Joan's acceleration to Sally's acceleration. So just kind of rearranging this, the acceleration of Joan divided by the acceleration of Sally will equal the time for Sally squared or the time for Joan squared. Just rearranging that formula right there. And so I would get the time for Sally, which is 300, squared, divided by the time for Joan, which is 250, squared. So the ratio of their accelerations is 300 squared divided by 250 squared. 1.44. No units on that, it's just a ratio between two quantities that have the same unit. So it's just a ratio. Joan is actually accelerating at 44% more than Sal. You kind of get an idea of how to approach these. I mean, we've actually done some of the harder ones here. there's a problem in the book, which I like to do. And I'm just going to describe it to you and we'll try it out. It's actually problem number 40 in chapter 2. On page 49. I'll read it to you and then we'll try it out. It says, Emily challenges her friend David to catch a dollar bill as follows. She holds the bill vertically as shown in figure 240 with the contact of the bill between David's index finger and thumb. David must catch the bill after Emily releases it without moving his hand downward. If his reaction time is 0.2 seconds, will he succeed? Explain your reasoning. See if I got any new dollar bills. Let's try this out. Now here's the challenge. You need a new dollar bill. I'm going to hold a dollar bill. I'm going to hold it between your index finger and thumb. And I'm going to drop it and see if you can catch it.
No.
Try this.
Without moving?
Without moving your hand downward. Pretty tough, huh? Yeah. I'll try it, Ricky. Really, you should try this with a higher denomination, but once in a while, somebody does grab it. So. Pretty tough. Let's try again. This is why you don't sit in the front row. You get put on the spot. Try it then. Pretty tough. Yeah. I noticed you lowered your hand, so it's going to hit down here to get grab it.
Yeah, I can get it quicker.
Wow, that's tough. Wait, you're not taking any studies. Actually pushed it down. Yeah, actually, I really don't understand why this is a problem, because I do it all the time. If you practice, it's really not a problem at all.
But your reaction time, look it up.
Oh,
It's about your reaction time.
yeah, it's all about reaction time. How can we figure out how fast you have to be in order to do this? All right, let's
Probably
figure this
better
out.
off just guessing. Now they're gonna drop it.
Yeah, that's why once in a while you lose your dollar bill. Somebody can react. Here's a dollar bill. Turns out the dollar bill, if I were to measure it, is 15.5 centimeters long. So this length here is 15.5 centimeters or 0.155 meters. If your friend puts their thumb and forefinger around the middle of the dollar bill, that means they have to grab this dollar bill within the time it takes for half the dollar bill to fall. So the distance we're talking about is a displacement, delta y, of 1/2 the length of the dollar bill, 1/2 L. So delta y is going to equal 0.155 meters divided by 2, or 0.0775. That's our delta y. We want to find the time it takes to follow that delta y. What else do we know? Acceleration, which it is? Positive 9.8 meters per second squared. We need to know another variable.
Initial velocity.
Initial velocity, which is 0. So there's our problem. Displacement given, acceleration given, initial velocity given. What is the time? So we could say that displacement equals initial velocity times time plus 1/2 acceleration times time squared. Of course, initial velocity is 0. Solve this for time, multiply both sides by 2, divide by acceleration, take the square root. So time will equal 2 times delta y, divided by acceleration, square root. So that's going to be 2 times 0.0775 divided by 9.8 square root. Let's figure out what that is. We'll round it up. So 0.126 seconds. 0.126 seconds. If you are a normal human being, your reaction time is probably about 0.22 seconds. 0.22 seconds. Maybe if you're really good, maybe about 0.2 seconds. If you're a drag racer, maybe slightly less than that. Maybe even 0.16 seconds or something. If you look at drag racing, I mean, and sometimes they get down to what is called reaction times of thousandths of a second, right? If you look at the top racers, they're trying to start as soon as they can without scratching, and they'll get down to start time of like 0.006 seconds. How do they do that?
They guess.
They guess. They anticipate, right? Because before it starts, you got I forget the progression of lights. The green, you have a red, and then the yellow, and then green. And you do that enough times, you kind of know the time spacing for each one. So if you anticipate when the next one's coming, you can actually increase your reaction time in relation to that. But it's actually just a guess. It's an anticipation. So if you didn't have a chance for that, you don't know when I'm going to drop this dollar bill. So you have no idea to anticipate. And so it's strictly, you have to react within 0.126 seconds. And so it's pretty good thing to do. So when you get your friends together, try this out. Now if you do this, make sure you only use dollar bills so that, if you say, if you catch it, you get the dollar bill, because then you don't feel so bad. And also use new dollar bills, because if they're crinkled or if they're bent like this, then air friction will kind of hold it up longer, and you could lose your money that way. So it could be very painful for you. So you want, if you have a whole dollar bill, just make sure it's kind of straight so that it'll just kind of slice down. Okay. I want to start something new today. Matt, do you know how to get me up on the computer over here?
Yeah.
We'll
Oh,
get-
Last week, finding the volume curve from the radio no, that wasn't here. No,
They would just do like this or wash your.
we did all, and there's like 3 or 4 of them, different methods to be shown. And he's like, you never have to do this, so it's completely unnecessary.
Hey, do you have problems?
No. I sure do not. Yeah, I'll do this.
Okay. I want to check on the list. I want to check for green everything for everything.
Okay.
Still on the green top of country.
Well, then, so probably for that.
Yes and no? No? Yes?
Yes.
Answer that for you. Vectors. In this chapter, we wish to look at vectors. Define scalar and vector quantities. Identify the properties of vectors. Some components of a vector and express it in vector form. Unit vector form. Add and subtract vectors. Everything to do with vectors. Why? Like anything in math, we wish to introduce the math so that you can do the physics. Physics is the interesting stuff. So we wish to introduce the vectors so that we can use them in order to talk about physics. Before we actually look at a vector itself, let's remind you what a polar coordinate system is. Say if I were to start with a Cartesian coordinate system, something like this, with the x and y axis, and then I actually have a point, x and y, on this coordinate system. I can also define that point in terms of 2 other variables. I can say that there is a line that starts from the origin to that point, and that length of that line has a certain length, which I'm going to call r. And say I can define that line also in terms of the angle theta from the positive x direction. So I can actually define this point from 2 other variables. A definite length from the origin, r, and a definite angle on the positive x-axis. So that these 2 variables, length and angle, r and theta, will describe this point just as well as these 2 variables, x and y. I call those two variables polar coordinate variables. And they relate to x and y. I can say that x is equal to r cosine theta, because if we look at this, there's a little right triangle here. And x is the adjacent side here. So x itself, the value of x is equal to the hypotenuse r times the cosine theta. And for that matter, I could also say that y is equal to r sine theta in the same right triangle here. And y divided by x would be r sine theta or r cosine theta, which would be tangent of theta. So with that in mind, I could say that theta is equal to the inverse tangent for the value of y over the value of x. This allows me, if I knew what x and y were, I could find out the angle theta and convert that to that. So I could get that variable. Continuing on, if I were to square the value x, I would get x squared equals r squared cosine squared theta. And do the same thing with y. Y squared equals r squared sine squared theta. So if I were to add the two, x squared plus y squared, I would get r squared times, in parentheses, cosine squared theta plus sine squared theta, which is a fancy name for what? So that's just 1. So that means x squared plus y squared equals r squared, which you know as to be the Pythagorean theorem. Or I could also write it like this: r equals the square root of x squared plus y squared. So again, if I knew what x was and what y was in the Cartesian coordinate system, I could find my value for r by the Pythagorean theorem: x squared plus y squared square root, get r. And now I've converted from x and y to r and theta, and those variables would just as well describe this point. Let's try this out. Here's an example, example 3.1. The Cartesian coordinates of a point are negative 3.5, negative 2.5. So x is negative 3.5, y is negative 2.5. We want to find the polar coordinates of this point. Well, I can find the value of r, because that's x squared plus y squared square root. That'll be a negative 3.5 squared plus negative 2.5 squared square root. 4.3 meters. So the value from the origin, the length from the origin will be 4.3 meters. And my angle theta will be the inverse tangent of the y component over the x component. Inverse tangent of negative 2.5 over negative 3.5, which will be 216 degrees from the positive x-axis. That will be an angle from this axis, 216 degrees. If you actually did this in your calculator would not give you 216 degrees. Right, Irvin? I'm figuring that's what you're doing right now.
35?
Or let's round it to 36.
Yeah,
36 degrees. That's because your calculator is not as smart as you are.
36.
Calculator does not know that both these values were negative values. So when it actually does the calculation, it assumes that this was a positive 2.5 over a positive 3.5. If you did that inverse tangent, you would get 36 degrees, which is exactly 180 degrees opposite from this. So you get the inverse tangent of the line up this way. So you have to be careful. The calculator is not always right. So we have to realize that this is in this third quadrant here, and so that's 180 degrees opposite. We have to add 180 degrees to it. Okay. Vectors and scalars. We define a scalar as something that has only magnitude, no direction. Examples are temperature. If I talk about the temperature in this room, I might say the temperature is 72 degrees Fahrenheit, and I would just say, well, that's the temperature. You know? Hopefully there's not too much variance in it, and if I just said that's the temperature of the room, that's the value of the room. It doesn't really depend on direction. The volume of this room is, I can figure out, height times width times depth, and figure out the volume. That'd be a definite number. Mass, a definite number, something, definite quantity. Doesn't depend on your direction. Energy, definite quantity of something. Work, we'll talk about that. That's actually a subset of energy. Time intervals. All these things are definite quantities of things. They don't necessarily depend on which direction you're going. They're just values. On the other hand, we define what we call a vector as a quantity that has magnitude and direction. Vectors are indicated in general by placing an arrow over the quantity or by indicating it by boldface type. So in this case, in my symbology, I would say that this is vector A, it's got the arrow above it, or it's bold. Vectors have magnitude and direction. They're indicated by an arrow graphically, and the length of the arrow indicates the magnitude of the vector, and the direction of the arrow indicates its direction in relation, in this sense, to the positive x direction. So it, in essence, is defined by polar coordinates, magnitude and direction. Examples would be displacement. In our discussion of displacement, there's definite magnitude involved, but it depends on whether I go that direction, or this direction, or that direction. So direction actually matters for displacement, where you actually go. It could be positive or negative, or if I think in 3 dimensions, it could be in any particular direction. Since displacement is a vector, so is velocity, because velocity is equal to your displacement over time. So velocity, by definition, is a vector divided by a scalar. And hence, it becomes a vector as well. Depends on whether, if I go 50 miles per hour to Birmingham, that's different from 50 miles per hour to Nashville. So velocity depends on direction. Acceleration is a vector as well, because acceleration is your change in velocity over time. So it is a vector divided by time. And for that matter, force would be a vector. As we'll see later on, force is equal to a scalar times acceleration. So it matters whether or not I push something, say, in this direction, or if I push it in that direction. The direction matters. I can give the same push in magnitude, but how I push it, what direction I push it, is important, and that makes it a vector quantity, magnitude and direction. Here's some properties of vectors. If I say vector A equals vector B, that means they have the same magnitude and the same direction. So the definition, they have the same length and the same angle from the positive x direction. They may or may not be on top of each other. They don't have to be. So in this case, A equals B. They're parallel with the same length. And I can say that. They have the same magnitude and direction. I can add 2 or more vectors tip to tail, and the resultant vector will be a vector that extends from the beginning of the first vector to the end of the last vector. So if I were to write this, I would say that vector A plus vector B added tip to tail plus vector C gets me over to here. That is the same as if I had just started right here at the origin and went straight to that point. So in terms of a vector sense, I could say that A plus B plus C is my resultant vector R. I would write it like this. Vector A plus vector B plus vector C equals R. And included in this is magnitude and direction. Now, this is easiest to see in terms of displacement. I mean, if I actually did this displacement, and that displacement, and that displacement, that would be the same as if I just started here and went straight there as a crow flies. But this would also include other quantities like velocities and acceleration. We add them tip to tail, sum equals the resultant. The negative of a vector is a vector that has the same magnitude, but 180 degrees opposite direction. So here's vector A, here's negative vector A, same magnitude vector, exactly 180 degrees opposite direction. I'll write this. I could write and say that vector A plus its negative vector A would be the same as A minus A, which mathematically might indicate 0, and vectorially it might indicate 0 because I can start here A, go up to here, to this point, then I add a negative A to that, so I start here and come back to where I started. So my total vector sum gets me back where I started. In other words, A minus A equals 0. I were to multiply a vector by a scalar quantity, if I were to say 2 times a, the effect is to increase or to change the magnitude of the vector by this scalar quantity. So 2 times a is the same as if I were to take 2 a's, add them together, tip to tail, and my result is 1 vector that's equal to 2a, twice the length. So any scalar multiple will just have the effect of increasing the length. Since vectors can be added tip to tail to create another vector, we can represent any two-dimensional vector in the xy plane as really the sum of 2 vectors. So we'll say that vector A here is the same as if I were to add 1 vector that's, I'll call it a sub x, that's totally in the x direction, plus another vector that's a sub y, totally in the y direction. This vector tip to tail plus this vector equals a. So I could write a as the sum of those 2 vectors. Vector A equals a sub x plus a sub y. One last thing here. We can define what we call unit vectors as vectors that have a specific direction. We're going to define I, j, and k as unit vectors. I that's totally in the x direction, j that's totally in the y direction, k that's totally in the z direction. And they all have magnitude 1. So their main purpose is to define direction, x, y, or z, I, j, and k. I can give them magnitude if I just multiply them by a number. So if I have these unit vectors at I, j, and k, if I multiply I by any scalar, I can give it a magnitude in that direction. And same thing with j and k. So if I had an arbitrary vector A in 3 dimensions, I could say it's actually the sum of 3 component vectors in the x, y, and z direction, something times I, plus something times j, plus something times k, and the sum of those 3 vectors would give me my vector A. Now, those vectors add tip to tail would give me my vector A. I could write it as a sub x times I plus a sub y times j plus a sub z times k. Some number times the unit vector plus some number times the unit vector plus some number times the unit vector. Scalars times these units will give me component vectors for that vector. I'm going to stop there, and we'll take this up again on Wednesday. But I have a present for you. I have a handout. Yeah, I just do that for administrative purposes, but I think we're pretty close to being even with that. As long as we have that. For those of you who have lab today, we're going to do a lab on gravity. We're going to drop a spigot fence through a photo gate. It is officially your easiest lab of all time. So when you find out that your lab doesn't take very long today, do not get spoiled and believe that all labs are going to be like that. But this one will be your easiest one.
Do you have to buy
All your labs this semester will be provided by